If you imagine there is a black hole space-time, so like the whole solution to Einstein's equation, and you treat you and me as what we call test particles. So we don't have any gravitational fields ourselves. We just move around in the gravitational field. And that's obviously an approximation, okay? But let's imagine that. And you stand outside the black hole and I fall in. And as I'm falling in, I'm waving to you, because I'm going into the black hole. You will see me move more and more slowly. And also the light from me is redshifted. So I kind of look embarrassed because I'm falling into a black hole. And there is a limit. There's a last moment that light will be emitted from me, from your perspective, forever. Okay. Now you don't literally see it because I'm emitting photons more and more slowly, right? Because from your point of view. So it's not like I'm equally bright. I basically fade from view in that picture. Okay. So that's one approximation. The other approximation is I do have a gravitational field of my own. And therefore, as I approach the black hole doesn't just sit there and let me pass through. It kind of moves out to eat me up because its net energy mass is going to be mine plus its. But roughly speaking, yes, I think so. I don't like to go to the dramatic extremes because that's where the approximations break down. But if you see something falling into a black hole, you see its clock ticking more and more slowly.
How do we know it fell in?
We don't. I mean, how would we? Because it's always possible that right at the last minute, it had a change of heart and starts accelerating away, right? If you don't see it pass in, you don't know. And let's point out that as smart as Einstein was, he never figured out black holes, and he could have. It's kind of embarrassing. It took decades for people thinking about general relativity to understand that there are such things as black holes, because basically Einstein comes up with general relativity in 1915. 2 years later, Schwarzschild, Carl Schwarzschild, derives the solution to Einstein's equation that represents a black hole, the Schwarzschild solution. No one recognized it for what it was until the 50s, David Finkelstein and other people. And that's just, one of these examples of physicists not being as clever as they should have been.
Well, that's the singularity. That's the kind of the edge of the theory, the limit. So it's understandable that it's difficult to imagine the limit of things.
It is absolutely hard to imagine, and a black hole is very different in many ways from what we're used to. On the other hand, I mean, the real reason, of course, is that between 1915 and 1955, there's a bunch of other things that are really interesting going on in physics, all of particle physics and quantum field theory. So many of the greatest minds were focused on that. But still, if the universe hands you a solution to general relativity in terms of curved spacetime, and it's kind of mysterious, certain features of it, I would put some effort into trying to figure it out.
So how does a black hole work? Put yourself in the shoes of Einstein and take general relativity to its natural conclusion about these massive things.
It's best to think of a black hole as not an object so much as a region of space-time, okay? It's a region with the property, at least in classical general relativity. Quantum mechanics makes everything harder, but let's imagine we're being classical for the moment. It's a region of space-time with the property that if you enter, you can't leave. Literally, the equivalent of escaping a black hole would be moving faster than the speed of light. They're both precisely equally difficult. You would have to move faster than the speed of light to escape from the black hole. So once you're in, that's fine. In principle, you don't even notice when you cross the event horizon, as we call it. The event horizon is that point of no return, where once you're inside, you can't leave. But meanwhile, the space-time is sort of collapsing around you to ultimately a singularity in your future, which means that the gravitational forces are so strong they tear your body apart, and you will die in a finite amount of time. The time it takes, if the black hole is about the mass of the sun, to go from the event horizon to the singularity takes about 1/1,000,000th of a second.
And what happens to you if you fall into the black hole? Like, if we think of an object as information, that information gets destroyed.
Well, you've raised a crucially difficult point. So that's why I keep needing to distinguish between black holes according to Einstein's theory of general relativity, which is book 1 of Space-Time and Geometry, which is perfectly classical. And then come the 1970s, we start asking about quantum mechanics and what happens in quantum mechanics. According to classical general relativity, the information that makes up you when you fall into the black hole is lost to the outside world. It's there, it's inside the black hole, but we can't get it anymore. In the 1970s, Stephen Hawking comes along and points out that black holes radiate. They give off photons and other particles to the universe around them. And as they radiate, they lose mass and eventually they evaporate, they disappear. So once that happens, I can no longer say the information about you or a book that I threw in the black hole or whatever is still there, it's hidden behind the black hole because the black hole has gone away. So either that information is destroyed, like you said, or it is somehow transferred to the radiation that is coming out, to the Hawking radiation. The large majority of people who think about this believe that the information is somehow transferred to the radiation and information is conserved. That is a feature both of general relativity by itself and of quantum mechanics by itself. So when you put them together, that should still be a feature. We don't know that for sure. There are people who have doubted it, including Stephen Hawking for a long time. But that's what most people think. And so what we're trying to do now in a topic which has generated many, many hundreds of papers called the black hole information loss puzzle is figure out how to get the information from you or the book into the radiation that is escaping the black hole.
Is there any way to observe Hawking radiation to a degree where you can start getting insight? Or is this all just in the space of theory right now?
Right now, we are nowhere close to observing Hawking radiation. Here's the sad fact. The larger the black hole is, the lower its temperature is. So a small black hole, like a microscopically small black hole, might be very visible. It's given off light. But something like the black hole at the center of our galaxy, 3 million times the mass of the sun or something like that, Sagittarius A star, that is so cold and low temperature that its radiation will never be observable. Black holes are hard to make. We don't have any nearby. The ones we have out there in the universe are very, very faint. So there's no immediate hope for detecting Hawking radiation.
Allegedly, we don't have any nearby.
As far as we know, we don't have any nearby.
Could tiny ones be hard to detect? Somewhere
Absolutely.
at the edges of the solar system, maybe?
So you don't want them to be too tiny or they're exploding, right? Or they're very bright and then they would be visible. But there's absolutely a regime where black holes are large enough not to be visible because the larger ones are fainter, right? Not giving off radiation, but small enough to not been detected through their gravitational effect. Yeah.
Psychologically, just emotionally, how do you feel about black holes? They scare you?
I love them. I love black holes. But the universe weirdly makes it hard to make a black hole. Right? Because you really need to squeeze an enormous amount of matter and energy into a very, very small region of space. So we know how to make stellar black holes. A supermassive star can collapse to make a black hole. We know we also have these supermassive black holes at the center of galaxies. We're a little unclear where they came from. I mean, maybe stellar black holes that got together and combined, but that's, one of the exciting things about new data from the James Webb Space Telescope is that quite large black holes seem to exist relatively early in the history of the universe. So it was already difficult to figure out where they came from. Now it's an even tougher puzzle.
So these supermassive black holes are formed somewhere early on in the universe. I mean, that's a feature, not a bug, right? That we don't have too many of them. Otherwise, we wouldn't have the time or the space to form the little pockets of complexity that we call humans.
I think that's fair. Yeah. It's always interesting when something is difficult but happens anyway, right? I mean, the probability of making a black hole could have been 0. It could have been 1, but it's this interesting number in between, which is kind of fun.
Are there more intelligent alien civilization than there are supermassive black holes?
Yeah. I have no idea, but I think your intuition is right that it would have been easy for there to be lots of civilizations, and then we would have noticed them already. And we haven't. So absolutely the simplest explanation for why we haven't is that they're not there.
Yeah. I just think it's so easy to make them, though. So there must be, I understand that's the simplest explanation. But also,
how easy is it to make life? Or eukaryotic life? Or multicellular life?
It seems like life finds a way. Intelligent alien civilizations, sure, maybe there is somewhere along that chain a really, really hard leap. But once you start life, once you get the origin of life, it seems like life just finds a way everywhere, in every condition. It just figures it out.
I mean, I get it. I get exactly what you're thinking. I think it's a perfectly reasonable attitude to have before you confront the data. I would not have expected Earth to be special in any way. I would have expected there to be plenty of very noticeable extraterrestrial civilizations out there. Um, but even if life finds a way, even if we buy everything you say, how long does it take for life to find a way? What if it typically takes 100 billion years? Then we'd be alone.
So it's a time thing. So to you, really, there's no alien civilizations out there. I can't see it. I believe there's
Yeah.
a ton of them, and there's another explanation why we can't see them.
I don't believe that very strongly. Look, I'm not going to place a lot of bets here. I would not. I'm both pretty up in the air about whether or not life itself is all over the place. It's possible when we visit other worlds, other solar systems, there's very tiny microscopic life ubiquitous, but none of it has reached some complex form. It's also possible there isn't any. It's also possible that there are intelligent civilizations that have better things to do than knock on our doors. So I think we should be very humble about these things we know so little about.
And it's also possible there's a great filter where there's something fundamental about once a civilization develops complex enough technology, that technology is more statistically likely to destroy everybody versus to continue being creative.
That is absolutely possible. I'm actually putting less credence on that one just because you need it to happen every single time, right?
Mm-hmm.
If even one, I mean, this goes back to John von Neumann pointed out that you don't need to send the aliens around the galaxy. You can build self-reproducing probes and send them around the galaxy. And you might think, well, the galaxy is very big. It's really not. It's some tens of thousands of light years across and billions of years old. So you don't need to move at a high fraction the speed of light to fill the galaxy.
So if you were an intelligent alien civilization, the dictator of one, you would just send out a lot of probes, self-replicating probes.
100%. And
just spread out.
Yes. And what you should do, so if you want the optimistic spin, here's the optimistic spin. People looking for intelligent life elsewhere often tune in with their radio telescopes, right? At least we did before Arecibo was decommissioned. That's not a very promising way to find intelligent life elsewhere, because why in the world would a super intelligent alien civilization waste all of its energy by beaming it in random directions into the sky? For one thing, it just passes you by, right? So if we're here on Earth, we've only been listening to radio waves for a couple hundred years, okay? So if an intelligent alien civilization exists for 1 billion years, they have to pinpoint exactly the right time to send us this signal. It is much, much more efficient to send probes and to park, to go to the other solar systems, just sit there and wait for an intelligent civilization to arise in that solar system. This is kind of the 2001 monolith hypothesis, right? I would be less surprised to find a sort of quiescent alien artifact in our solar system than I would to catch a radio signal from an intelligent civilization.
So you're a sucker for in-person conversations versus remote.
I just want to integrate over time. A probe can just sit there and wait, whereas a radio wave goes right by you.
How hard is it for an alien civilization, again, you're the dictator of one, to figure out a probe that is most likely to find a common language with whatever it finds?
Couldn't I be like the elected leader of
elected
the alien
leader,
civilization?
democratic leader, elected leader of a democratic alien civilization? Yes,
I think we would figure out that language thing pretty quickly. I mean, maybe not as quickly as we do when different human tribes find each other, because obviously there's a lot of commonalities in humanity, but there is logic and math, and there is the physical world. You can point to a rock and go, rock, right? I don't think it would take that long. I know that Arrival, the movie, based on a Ted Chiang story, suggested that the way that aliens communicate is going to be fundamentally different. But also they had precognition and other things I don't believe in. So I think that if we actually find aliens, that will not be our long-term problem.
So there's a folks one of the places you're affiliated with is Santa Fe, and they approach the question of complexity in many different ways,
Mhm.
and ask the question in many different ways of what is life, thinking broadly. So to you would be able to find it. You'll think you show up, a probe shows up to a planet, we'll see a thing and be like, yeah, that's a living thing.
Well, again, if it's intelligent and technologically advanced, the more short-term question of if we get, some spectroscopic data from an exoplanet, so we know a little bit about what is in its atmosphere. How can we judge whether or not that atmosphere is giving us a signature of life existing?
Mhm.
That's a very hard question that people are debating about. I mean, one very simple-minded, but perhaps interesting approach is to say small molecules don't tell you anything because even if life could make them, something else could also make them. But long molecules, that's the kind of thing that life would produce.
So signs of complexity.
Hmm.
I don't know. I just have this nervous feeling that we won't be able to detect it. We'll show up to a planet, there'll be a bunch of liquid on it. We like we take a swim in the liquid, and we won't be able to see the intelligence in it. Whether that intelligence looks like something like, ants, or
Mm.
we'll see movement,
Mm.
perhaps strange movement, but we won't be able to see the intelligence in it or communicate with it. I guess if we have nearly infinite amount of time to play with different ideas, we might be able to.
I'm in favor of this kind of humility, this intellectual humility that we won't know because we should be prepared for surprises. But I do always keep coming back to the idea that we all live in the same physical universe. And if, well, let's put it this way. The development of our intelligence has certainly been connected to our ability to manipulate the physical world around us. And so I would guess, without 100% credence by any means, but my guess would be that any advanced kind of life would also have that capability. Both dolphins and octopuses are potential counterexamples to that. But I think in the details, there would be enough similarities that we would recognize it. I have my process traditionally was I was working in this general area of particle physics, field theory, general relativity, cosmology, and I would sort of try to take things other people were talking about and ask myself whether or not it really fit together. Like my so I guess I have 3 papers that I've ever written that have done super well in terms of getting cited and things like that. One was my first ever paper that I get very little credit for. That was my advisor and his collaborator, set that up. The other 2 were basically my idea. One was right after we discovered that the universe was accelerating. So in 1998, observations showed that not only is the universe expanding, but it's expanding faster and faster. So that's attributed to either Einstein's cosmological constant or some more complicated form of dark energy, some mysterious thing that fills the universe. And people were throwing around ideas about this dark energy stuff. What could it be? And so forth. Most of the people throwing around these ideas were cosmologists. They work on cosmology. They think about the universe all at once. Since I like to talk to people in different areas, I was sort of more familiar than average with what a respectable working particle physicist would think about these things. And what I immediately thought was, you guys are throwing around these theories. These theories are wildly unnatural. They're super finely tuned. Like any particle physicist would just be embarrassed to be talking about this. But rather than just scoffing at them, I sat down and asked myself, okay, is there a respectable version? Is there a way to keep the particle physicists happy, but also make the universe accelerate? And I realized that there is some very specific set of models that is relatively natural. And guess what? You can make a new experimental prediction on the basis of those. And so I did that. People were very happy about that.
What was the thing that would make physicists happy, that would make sense of this fragile thing that people call dark energy?
So the fact that dark energy pervades the whole universe and is slowly changing, that should immediately set off alarm bells, because particle physics is a story of length scales and time scales that are generally, guess what? Small, right? Particles are small, they vibrate quickly. And you're telling me now I have a new field and its typical rate of change is once every billion years, right? Like that's just not natural. And indeed, you can formalize that and say, look, even if you wrote down a particle that evolved slowly over billions of years, if you let it interact with other particles at all, that would make it move faster. Its dynamics would be faster. Its mass would be higher, et cetera, et cetera. So there's a whole story. Things need to be robust and they all talk to each other in quantum field theory. So how do you stop that from happening? And the answer is symmetry. You can impose a symmetry that protects your new field from talking to any other fields, okay? And this is good for two reasons. Number one, it can keep the dynamics slow. So if you can't tell me why it's slow, you just made that up, but at least it can protect it from speeding up because it's not talking to any other particles. And the other is it makes it harder to detect. Naively, experiments looking for fifth forces or time changes of fundamental constants of nature like the charge of the electron, these experiments should have been able to detect these dark energy fields. And I was able to propose a way to stop that from happening.
The detection,
yeah. Because a symmetry could stop it from interacting with all these other fields and therefore makes it harder to detect. And just by luck, I realized, because it was actually based on my first ever paper, there's one loophole. If you impose these symmetries, so you protect the dark energy field from interacting with any other fields, there's one interaction that is still allowed that you can't rule out. And it is a very specific interaction between your dark energy field and photons, which are very common. And it has the following effect. As a photon travels through the dark energy, the photon has a polarization, up, down, left, right, whatever it happens to be. And as it travels through the dark energy, that photon will rotate its polarization. This is called birefringence. And you can kind of run the numbers and say, you can't make a very precise prediction because we're just making up this model. But if you want to roughly fit the data, you can predict how much polarization rotation there should be. A couple of degrees, okay? Not that much. So that's very hard to detect. People have been trying to do it. Right now, literally, we're on the edge of either being able to detect it or rule it out using the cosmic microwave background. And there is just, truth in advertising. There is a claim on the market that it's been detected, that it's there. It's not very statistically significant. If I were to bet, I think it would probably go away. It's a very hard thing to observe. But maybe as you get better and better data, cleaner and cleaner analysis, it will persist and we will have directly detected the dark energy.
So if we just take this tangent of dark energy, people will sometimes bring up dark energy and dark matter as an example why physicists have lost it, lost their mind. We're just going to say that there's this field that permeates everything, is unlike any other field, and it's invisible. And it helps us work out some of the math. How do you respond to that? Those kinds of suggestions?
Well, two ways. One way is those people would have had to say the same thing when we discovered the planet Neptune.
Yeah.
Because it's exactly analogous, where we have a very good theory, in that case, Newtonian gravity in the solar system. We made predictions. The predictions were slightly off for the motion of the outer planets. You found that you could explain that motion by positing something very simple, one more planet in a very, very particular place. And you went and looked for it, and there it was, right? That was the first successful example of finding dark matter in the universe.
It's a matter that we can't see.
Neptune was dark.
Yeah.
There's a difference between dark matter and dark energy, right? Dark matter, as far as we are hypothesizing it, is a particle of some sort. It's just a particle that interacts with us very weakly. So we know how much of it there is. We know more or less where it is. We know some of its properties. We don't know specifically what it is. But it's not anything fundamentally mysterious. It's a particle. Dark energy is a different story. So dark energy is indeed uniformly spread throughout space, and has this very weird property that it doesn't seem to evolve as far as we can tell. It's the same amount of energy in every cubic centimeter of space from moment to moment in time. That's why far and away the leading candidate for dark energy is Einstein's cosmological constant. The cosmological constant is strictly constant, 100% constant. The data say it had better be 98% constant or better. So 100% constant works, right? And it's also very robust. It's just there. It's not doing anything. It doesn't interact with any other particles. It makes perfect sense. Probably the dark energy is the cosmological constant. The dark matter, super important to emphasize here. It was hypothesized at first in the 70s and 80s, mostly to explain the rotation of galaxies. Today, the evidence for dark matter is both much better than it was in the 1980s and from different sources. It is mostly from observations of the cosmic background radiation or of large-scale structure. So we have multiple independent lines of evidence, also gravitational lensing and things like that, many, many pieces of evidence that say that dark matter is there. And also that say that the effects of dark matter are different than if we modified gravity. So that was my first answer to your question is dark matter, we have a lot of evidence for. But the other one is, of course, we would love it if it weren't dark matter. Our vested interest is 100% aligned with it being something more cool and interesting than dark matter, because dark matter is just a particle. That's the most boring thing in the world.
And it's non-uniformly distributed through space, dark matter?
Absolutely, yeah.
And so
you can even see maps of it that we've constructed from gravitational lensing.
So verifiable sort of clumps of dark matter in the galaxy that explain stuff.
Bigger than the galaxy, sadly. Like, we think that in the galaxy, dark matter is lumpy, but it's weaker. Its effects are weaker. But on the scale of large-scale structure and clusters of galaxies and things like that, yes, we can show you where the dark matter is.
Could there be a super cool explanation for dark matter that would be interesting as opposed to just another particle that sits there in clumps?
The super cool explanation would be modifying gravity rather than inventing a new particle. Oh. Sadly, that doesn't really work. We've tried. I've tried. That's my third paper that was very successful. I tried to unify dark matter and dark energy together. That was my idea. That was my aspiration, not even idea. I tried to do it. It failed even before we wrote the paper. I realized that my idea did not help. It could possibly explain away the dark energy, but it would not explain away the dark matter. And so I thought it was not that interesting, actually. And then two different collaborators of mine said, has anyone thought of this idea? Like, they had thought of exactly the same idea completely independently of me. And I said, well, if three different people found the same idea, maybe it is interesting. And so we wrote the paper. And yeah, it was very interesting. People are very interested in it.
Can you describe this paper a little bit? Like, it's fascinating how much of a thing there is, dark energy and dark matter, and we don't quite understand it. So what was your dive into the exploring how to unify the two?
So here is what we know about dark matter and dark energy. They become important in regimes where gravity is very, very, very weak. That's kind of the opposite from what you would expect if you actually were modifying gravity. Like, there's a rule of thumb in quantum field theory, et cetera, that new effects show up when the effects are strong, right? We understand weak fields, we don't understand strong fields. But okay, maybe this is different, right? So what do I mean by when gravity is weak? The dark energy shows up late in the history of the universe. Early in the history of the universe, the dark energy is irrelevant. But remember, the density of dark energy stays constant. The density of matter and radiation go down. So at early times, the dark energy was completely irrelevant compared to matter and radiation. At late times, it becomes important. That's also when the universe is dilute and gravity is relatively weak. Now think about galaxies, okay? A galaxy is more dense in the middle, less dense on the outside. And there's a phenomenological fact about galaxies that in the interior of galaxies, you don't need dark matter. That's not so surprising because the density of stars and gas is very high there, and the dark matter is just subdominant. But there's generally a radius inside of which you don't need dark matter to fit the data, outside of which you do need dark matter to fit the data. So that's, again, when gravity is weak, right? So I asked myself, Of course, we know in field theory, new effects should show up when fields are strong, not weak, but let's throw that out of the window. Can I write down a theory where gravity alters when it is weak? And we've already said what gravity is. What is gravity? It's the curvature of spacetime. So there are mathematical quantities that measure the curvature of spacetime. And generally, you would say, like, I have an understanding. Einstein's equation, which I explained to the readers in the book, relates the curvature of spacetime to matter and energy. The more matter and energy, the more curvature. So I'm saying, what if you add a new term in there that says the less matter and energy, the more curvature? No reason to do that, except to fit the data, right? So I tried to unify the need for dark matter and the need for dark energy.
That would be really cool if that was the case. Like,
super cool, right? It'd be the best. It'd be great.
but
it didn't work.
It'd be really interesting if gravity did something funky when there's not much of it. Like almost like at the edges of it, it gets like noisy.
That was exactly the hope, right? But the great thing about physics is there are equations, right? I mean, you can come up with the words and you can wave your hands, but then you got to write down the equations, and I did. And I figured out that it could help with the dark energy, the acceleration of the universe. It doesn't help with dark matter at all. Yeah.
It just sucks that at the scale of galaxies and scale of solar systems, the physics is kind of boring.
Yeah, it does. I agree. Again, that's why it is a little bit, I tear my hair out when people who are not physicists accuse physicists, like you say, of sort of losing the plot because they need dark matter and dark energy. I don't want dark matter and dark energy. I want something much cooler than that. I've tried, but you got to listen to the equations and to the data.
You mentioned 3 papers. Your first awesome paper ever, and your second awesome paper ever. Of course, you wrote many papers, so you're being very harsh on the others. But
well, by the way, this is not awesomeness. This is impact.
Impact,
right?
Sure.
There's no correlation between awesomeness and impact.
Right.
Some of my best papers fell without a stone.
Tree
and vice
falls
versa,
in the forest.
Right? Yeah. The first paper was called Limits on a Lorentz and Parity Violating Modification of Electromagnetism, or Electrodynamics. So we figured out how to violate Lorentz invariance, which is the symmetry underlying relativity. And the important thing is we figured out a way to do it that didn't violate anything else and was experimentally testable. So people love that. The second paper was called Quintessence and the Rest of the World. So quintessence is this dynamical dark energy field. The rest of the world is because I was talking about how the quintessence field would interact with other particles and fields and how to avoid the interactions you don't want. And the third paper was called Is Cosmic Speed Up Due to Gravitational Physics? Something like that. So you see the common theme. I'm taking, what we know, the standard model of particle physics, general relativity, tweaking them in some way, and then trying to fit the data.
And trying to make it so it's experimentally validated.
Ideally, yes, that's right. That's the goal.